Hi Math 30-1. So today we're going to look at rational functions. So before we get started, we're actually going to draw the graph y equals x because we're going to use it to compare the graph y equals 1 over x. So y equals x is going to look something like this. It's a linear line, okay, looking something like that. So now what I want you to do is you're going to take your graphing calculator and you're going to graph y equals 1 over x. And if you graph y equals 1 over x on your graphing calculator, you should end up with a graph that looks something like this. So there's a few things I'm going to get you to pay attention to. Let's use the sparkly one. Yay, sparkles. So the first thing is hopefully you're kind of noticing that there is an asymptote along the y-axis for this graph. The reason being is because you can't divide by 0. So the graph cannot equal 0 when x equals 0, so that's why there's an asymptote there. There's also a horizontal asymptote on the line y equals 0, which we're going to get into a little bit later here. First of all, what is an asymptote? We always have this question. Our kids aren't quite sure what an asymptote means. So I have a lot of kids who have the misconception where they think an asymptote is a line or imaginary line that your graph never crosses. That's actually sometimes true, but not always the case. So an asymptote is actually an imaginary line in which your graph approaches towards infinity. So if you look at this graph, okay, it's approaching closer and closer to that asymptote, and in this case it doesn't cross, it's approaching that asymptote towards infinity. Even along the x-axis here, it's approaching that x-axis towards infinity. So that's why we have both a vertical and a horizontal asymptote in this particular graph. Now the other thing I hope you noticed, and I'm going to use a highlighter this time. Ooh, let's go purple. Okay. Here's the little owl, and he says, do you notice any invariant points? So when you graph these two graphs, there should have been 2 points that were in common. So when y equals 1 and when y equals -1. The reason being is if you were to take 1 over 1, you would end up with +1, right? So you'd end up back to where you started, which is what an invariant point is. It means that your graph actually didn't change at that point. If you were to take 1 over -1, you would end up with -1. Okay, so once again, that y value did not change, therefore making it an invariant point of this graph. So, oh dear, I'm actually going to skip ahead here because it looks like my graph disappeared for some reason. Or can I make it go back? What happened to it? I don't know. You know what? We'll just graph it anyways. Let's graph it on an imaginary graph here. Okay, so if I were to graph my original function of y equals x minus 5, I would have a graph that looked something like this. So it's going to have a y-intercept at -5 and an x-intercept at +5. Now on your calculator, try to graph 1 over x minus 5. If you graph 1 over x minus 5, you should notice a graph that looks something like this. So I'm going to have that vertical asymptote, okay, where that x-intercept was because x can equal 0. And then my graph will look something along this lines. So once again, you can see that that graph is approaching that vertical asymptote towards infinity. And also with this graph, you'll notice that it has a horizontal asymptote at y equals 0 because it's approaching the x-axis towards infinity. There are invariant points on this graph, and I'm going to draw them out really quickly here, where y equals +1 and where y equals -1. So if I were to write my domain and range of this graph, my domain would be, for all x values, x is an element of all real numbers. However, x cannot equal +5. My range would be for all y values. Y is an element of all real numbers. However, y cannot equal 0 because that's where the horizontal asymptote is in this case. Okay, so let's try to graph this one. Again, we're going to graph it on our graphing calculator. However, without our graphing calculator, if we remember our quadratic function unit from Math 20-1, we will notice that there is a vertex on this graph when x is positive 6 and y is negative 2. So if I were to go to x is positive 6 and y is negative 2, I'd have my vertex right there. Okay, and then I also will notice when I graph this that I have x-intercepts at 4 and 8. So it's going to look something like this. All right, so if you were to graph the rational expression, or the reciprocal of this graph, you'd have 1 over 2, bracket x minus 6 squared minus 2. When you're trying to graph rational functions, make sure that you're putting the numerator and denominator in brackets, or you will end up with a different graph. So to start with, on my graph, I'm going to have asymptotes whenever x equals 0, or y equals 0. So there's going to be an asymptote when x is positive 4, and also when x is positive 8. Your graph is going to approach that asymptote. So it's going to look something like this. So it's approaching the asymptote on both sides. Now, if you ever wanted to know how to draw the graph, you could take any y value and just put 1 over that y value. So here on my vertex, I have a y value of negative 2. So if I wanted to know where the new point would be after taking the reciprocal, I would just go 1 over negative 2, which would give me negative 0.5. So my new point would be at negative 0.5, and then from there it's just going to approach that asymptote on both sides. And again, you could draw this on your graphing calculator as well. So now to write my domain and range, my domain would be for all x values, x is any real number. However, x cannot equal positive 4 or positive 8. And my range would be for all y values, y is any real number. However, y cannot equal 0. Okay, and you could draw your invariant points on this graph too. They're going to be when y equals positive 1. I didn't do a very good job of drawing this. So there's 2 places there, and when y equals negative 1. There'd be 4 invariant points on this graph. All right, so now actually we're going to start looking at how to find asymptotes using not just our graph, but actually looking at the function itself. Okay, but before we do that, we're going to look at a few rules. So first of all, vertical asymptotes. Generally speaking, algebraically we can find the equations of vertical asymptotes by finding the zeros of the denominator. And then it gives you an example there. So here in this example, we see the denominator is x minus 3, bracket x minus 2. So vertical asymptotes are really any factors in our denominator that don't cancel out. Okay, so it's easiest to find vertical asymptotes when your rational expression is in factored form. Horizontal asymptote, there's actually 3 rules that apply. And sometimes the best way to remember these rules is to think of an example. So if the degree of the numerator is less than the denominator, the horizontal asymptote is y equals 0. So the easiest example is if we had the degree of the numerator is less than the degree of the denominator, so 1 over x. So I know my degree of my numerator, it's just a constant that really is no degree. Okay, and the degree of my denominator would be 1. If you were to graph 1 over x, you'd end up with a horizontal asymptote of y equals 0. If the degree of the numerator is equal to the degree of the denominator, then we divide the leading coefficients. So for example, if you had 3x over 2x, they both have a degree of 1, so then you would just divide the leading coefficients. So my horizontal asymptote would be at 3 over 2. If the degree of the numerator is greater than the degree of the denominator, for example, if you had x over 1, okay, there would be no horizontal asymptote. If you were to graph y equals x over 1, there'd be no horizontal asymptote there. All right, so let's look at this example here. So first, what you're going to do is when you're looking at these types of questions, we're going to factor. Okay, so what are two numbers that multiply to give us -6 and add to give us +1? And we need to write our function just so that our notation is there. X plus 3 times x minus 2. What are two numbers that multiply to give me, this time I'm going to have to use decomposition. So I'm going to need to multiply 2 times 3, which gives me -6. So two numbers that multiply to give me -6 and add to give me -1 are positive 2x and negative 3x. All right, and then we can factor both sides here. So on the left side, I can take out a 2x, which would leave me with x plus 1. On the right side, I can take a -3 out, which leaves me with x plus 1. So then I end up with 2x minus 3 times x plus 1. So that is that trinomial in factored form. So I have 2x minus 3 bracket x plus 1. So from here I can find my vertical asymptotes. So my first vertical asymptote, okay, is the 0 of the factor x plus 1. So the 0 of the factor of x plus 1 would be -1. So my first vertical asymptote would be when x equals -1. My second vertical asymptote, I would take the 0 of 2x minus 3. And if you're not sure what that is, just by looking at it on the side of your paper, you could actually make it equal to 0 and then solve for it. So in this case, my vertical asymptote would be x equals 3 over 2. The horizontal asymptote is actually easiest to find when you're in expanded form, not factored form. So when we look at this rational expression or rational function in expanded form, we notice that the degree of the numerator is 2 and the degree of the denominator is 2, so they have an even degree. If you go back to your rules, when you have an even degree, you divide the leading coefficients. So here my leading coefficient would be 1, and here my leading coefficient would be 2. So then that means in this graph, my horizontal asymptote would be at y equals 1 over 2. All right, and those are all my asymptotes. So it's actually a lot easier to find them algebraically using those rules than it is to look at your graphing calculator. Okay, so from here, before we jump back to this slide, we're actually going to look really quickly at another quick rule. So, asymptotes, we have vertical and horizontal. There's also holes in the graph. So when you have a graph where, let's say you had a denominator of x minus 3, but it ends up canceling out, okay, instead of being a vertical asymptote, you actually will end up having a hole in the graph, okay, or you will see it called a point of discontinuity. All right, so in this case, this actually would not be a vertical asymptote. So vertical asymptotes are only when you have your factors in the denominator and that they don't cancel out. So let's backtrack here, and we're actually going to try to graph all of these. So what I'm going to do is I'm just going to graph the first one with you, just to show you a couple of things, and then I'll get you to graph them all by yourself here. So, oops. So I'm going to go to my graphing calculator. I already have this typed in. Make sure, again, when you're graphing rational expressions, you need to make sure that the numerator and denominator are both in brackets, or else your graph's not going to work. So if you type this in your calculator and then you press graph, you're going to see a straight line, and you're like, well, that looks like a linear graph. Okay, but if you go to your table of values, you will notice that there's a hole in the graph. And I'm going to show you where that hole is. Oops. Okay, so when x is -1, on my calculator it says nil, on yours it might say error. But that would be a hole in the graph because there is no y value when x is -1. It's still a restriction or a non-permissible, but instead of an asymptote, it is a hole in the graph, and that's why you can't really see it on the graph. Okay, so let's draw that out then. And when I draw my hole in the graph, I'm just going to draw my line and draw a little open dot there just to show the hole in the graph. And it's going to look something like that. So let's go ahead and factor this. So we know that this numerator is a difference of squares, so it's the same as x minus 1, x plus 1. You know what, I'm running out of room, so I'm going to write it up here. X minus 1, x plus 1, all over x plus 1. There we go. So in this case, the x plus 1's cancel out, which means you have that hole in the graph. So there is no vertical asymptote, so you're going to write none. If you look at this graph, does it look like there's a horizontal asymptote? No. And if you go back to the rules, the degree of the numerator is higher than the degree of the denominator, which means there's no horizontal asymptote. However, there is a non-permissible because of that hole in the graph, so we would say x cannot equal -1. All right, so now we're going to graph this next one. And again, you can type this in your graphing calculator. You'll end up with the hole in the graph again. If we factor this, we end up with two numbers that multiply to give me -2 and add to give me +1 are x plus 2, x minus 1, all over x plus 2. So again, the x plus 2 cancels out, so we have another hole in the graph, so there are no vertical asymptotes. And because it looks like a linear graph, and when you think of your rules with horizontal asymptotes, the degree of your numerator is higher than the degree of your denominator, there are no horizontal asymptotes. However, that hole in the graph is a non-permissible, so I would write x cannot equal -2. Okay, my next one, I can factor in -2 out, and I'd end up with x minus 2 all over x minus 1. So nothing cancels out here, so I should see a vertical asymptote on this graph. So if I graph this, I end up with a graph that looks like this. So you can see there is a vertical asymptote, and it's where x equals 1, because that is the factor, or the 0 of the factor on my denominator. You will also notice there's a horizontal asymptote. So notice how the degree of the numerator is the same as the degree of the denominator. So that's when I divide the leading coefficients. So -2 divided by 1, because I'm going to put a 1 there, is -2. So my horizontal asymptote would be when y equals -2. My non-permissible values of x, in this case, would just be that vertical asymptote, so x cannot equal +1. Last graph. Type it in our graphing calculator. You should end up with a graph that looks like this. So you can see those vertical asymptotes here, and I'll draw them in yellow really quick. Right there and right there. So in this case, if we factor that denominator, I'm going to take a negative out of it, which will flip my signs. Two numbers that multiply to give me -3 and add to give me -2 are -3 and +1. So then my new rational expression is just 2 over -x minus 3 and x plus 1. So then my vertical asymptotes would be x equals -1 and x equals +3 because those are the zeros of the factors on my denominators. The horizontal asymptote, in this case, the degree of the denominator is higher than the degree of the numerator, so my horizontal asymptote would be y equals 0. And then my non-permissibles would just be those vertical asymptotes. So y cannot equal -1, x cannot equal -1, and x cannot equal 3. All right.